Right, so this morning we were finishing with this. I was giving you this example. And we were talking about this model. Right, so essentially you can view this whole thing here. Right, this essentially, if you like, this is the equivalent channel of the direct path plus the RIS, plus the intelligent surface, right? So this is called reconfigurable intelligent surfaces because you can really change the phase shift across each of those elements, or in other words, you can really change the entries of this matrix theta, right? And that's why the reconfigurability comes from. Right, so what we're going to do now, I will show you an example of how you could optimize the W and this theta, you know, to maximize some objective function. And in your project, in your coursework 3, you're going to do this, something very similar to this, but it's going to be an extension to a multi-user scenario, right? It's multi-user, right? So instead of having only one receiver, you're going to have multiple receivers. So the system model will be a bit more complicated. Right, but essentially what you're going to do is that you're going to reuse all the stuff we did this morning and a few weeks ago. And you're going to reuse some of the development or the tools that actually we're going to do now. Okay, so first question, and this is, you know, you can argue this is quite relatively easy for this setup, is how would you choose W typically if you want to maximize the performance? And the performance would be, for instance, maximizing SNR. Right? If you want to maximize the SNR, and this is your equivalent channel, you have a system model that says, okay, I have a Y, H, W, I write X, plus N. If I want to maximize my SNR, how do I choose W? Should all know this. MRC or MRT, right, at the transmission. So you do maximum ratio transmission, right? So essentially, you will have your W is H emission, and you can normalize it to keep the transmit power equal to 1. Now, what is our H now? Or H, the equivalent H is this one, HR theta G plus HD. Right? This is now our H, effectively. Okay, so what you can do is you can design your transmit precoder according to this channel. Right? And you would do this assuming that, well, this is obtained for a given value of theta. Right? So for given theta, you can say, okay, I will do maximum ratio transmission here so that I maximize the SNR. Is that here? Right, I maximize the SNR for a given value of theta. And if the theta change, then the W will change as well. Okay, so this is what I'm doing here. I'm saying, well, we do maximum ratio transmission. Right? So let's do maximum ratio transmission. And so if you do maximum ratio transmission, after precoding, you're going to have a SNR that is proportional to the norm of H squared, right? And this is something we've done on many lectures ago. So in other words, because H is given by this, you're going to have an SNR that is proportional to the norm of this square, right? And this is where things comes in. So now I end up with a problem where if I want to maximize my SNR, I will choose my precoder at the base station according to maximum ratio transmission. But I'm still left with choosing this theta, right? So I still have to maximize the SNR or choose the theta in order to maximize the SNR. So I know how to choose the W, but I don't know yet how to choose the theta, right? So this is the second question, which is now the more difficult part, because I need to maximize this term, but I have some constraint on the theta. So what is this theta? I was saying this morning, this theta is a diagonal matrix. So I have theta is now a diagonal matrix where each entries on the diagonal is a phasor. So it's just a complex exponential, right? So that's this entry that you have on each of those elements. So you have n elements, right, in this RIS, and each of them, what they do is that they actually create a phase shift. So you can model this as now a diagonal theta here, where the diagonal comes from the fact that each element, the wave is impinging on each of those elements, and each of those elements reflect all the wave back, but just change the phase shift. Right. Okay, so this is the problem I have. And this theta is diagonal, and I change the notation a little bit. You see, I write this theta 1. So let me say this is maybe a phi, right? Phi n. So this is called theta. So this is theta 1, right? And because those theta here are complex exponential, the magnitude is equal to 1. Okay, so you evolving on a complex field where the magnitude is equal to 1. So you are here. Right? Is this convex? So you're on the unit circle, not the disk, right? You cannot be inside. You're on the circle. Is this convex? No. Right? You take any 2 points here on this, you draw the line, that will not belong to this set, right? So this constraint here, this very naive constraints, also really kills the whole convexity of the problem, right? So this becomes a non-convex problem, right? So what we do here, and this was done in this paper just 2-3 years ago, we essentially try to transform the problem in order to end up with a semi-definite program or semi-definite relaxation. And so how you do that, you see that this theta that you want to optimize, it's a bit stuck in between those two matrices. Right? So what you try to do is that you try to reformulate so that this theta comes out, either on the left side or the right side, but comes out, because what I want to do, I want to have a formulation that looks like something like this. X Hermitian are X. And then I would say, oh, this is a trace of this. And then this is a trace of something like this. Right? I'm always using the same trick, right? And then I'm saying, okay, this is a trace of a big matrix. And I'm saying the X has to be positive semi-definite. And then I'm saying the rank of X is equal to 1. Right? This is where I want to get to. Right? But it doesn't look like this, right? When you see this formulation, you're very far away from something like this. So here the first step, you say, okay, let me take those diagonal elements of this theta, and I just create a vector. And then this is a row vector. This is a diagonal matrix. So what I can do, I can switch the order by saying the diagonal element here, I create just a row vector. And now this vector here, the entry of this row vector, becomes the diagonal entries of this diagonal matrix. And by doing so, you actually don't change anything, but what is interesting is that now your theta is on the left side, so now you have now a concatenated kind of matrix that is just a function of the channel from the transmitter to the RIS, and from the RIS to the receiver, right? So this is interesting because now you can take this formulation and you can expand this, and you can expand and you see that you have this kind of quadratic form that appears where your theta is what you want to essentially find, because that contains all those diagonal elements of this big theta. this phi matrix here is just channel state that is given. You assume known. You assume perfectly known everywhere. And now you have 3 terms there, 4 terms, right? So if you want to maximize this, you see that this last term is not a function of theta, so you could argue I can get rid of this. It does not really matter, right? Because if you remove this, well, the theta that maximizes this, whether you have this or not, does not change anything. Right. So this would be your objective function, and you're subject to this constraint now that all those entries of this theta here has to be equal to 1. Okay? So this would be a quadratic program. This is clearly a quadratic program with which is non-convex because of the constraint there, right? So let's try to formulate this in something like this. So I want to take this expression here, but I want to change this so that it looks like something like this. Okay, so in other words, I want to make it homogeneous in the sense that I get rid of all these kind of terms here that are only dependent on theta. And the reason I want to do this is because if I can get rid of all those kind of terms, then I have this simplicity here. I can move this x on one side and use a trace and then end up with the formulation that we have in SDP. Okay, so the trick we're using here is the same as the one we used in the MIMO detection. So we introduce now another variable t, same trick, where the expression I had before, this one, can now be written equivalently by as follows, as this, where in this v contains a theta, but also another variable t. And now in this matrix R, I have those different entries that I had in this quadratic form. So I had here, this forms one block of my matrix R. This would be another block. This would be another block, and so on. Right? So I'm reformulating this such that my objective function now looks like completely homogeneous. It's still a quadratic program, objective function, but it's completely homogeneous. I don't have any other terms there. And this quantity is strictly equivalent to what we had before. Now what I have here, those v, and the t has to be, magnitude has to be equal to 1, but I will not go into those details today. You will see this when you start working on your coursework 3. But what is important is that your theta here, the magnitude of each of those entries has to be equal to 1, right? So this is still reflected here by the entries of this vector v. The magnitude has to be equal to 1. Okay, so this is okay, this is fine, this is something that we are familiar with, looks like this, but this is still not okay, this is still non-convex. Right? So how can I change this? Well, I want to essentially get rid of this absolute value here, right? So what I can do now, I can say, well, I have my v. If I take the same notation, I have the VH remission, right? And now I have this. And I have VHV. And now I'm creating a matrix X here that is equal to this, where the diagonal entries of X will be the magnitude square of the entries of V, right? The entries of V, the magnitude is equal to 1, so that makes the magnitude square of the entries here on the diagonal have to be equal to 1, right? So this is what I have here. The diagonal entries of this have to be equal to 1 because those ones here, the magnitude is equal to 1, right? So this is what I have there. So now I have my X, or I'll write the same as there. I have a big matrix V, right? This is semi-definite positive. So I create a matrix V that is now semi-definite positive. It's there. But this has to be rank 1. because this is rank 1, so this is what I have there, rank 1. And now those diagonal entries of V, they have to be equal to 1 because each of those entries here have a magnitude equal to 1, right, coming from this constraint. Okay, so now we have something that we like. This is linear in the entries of V. This is just linear in the entries of V. This is a semi-definite constraint, a semi-definite positive constraint. And this is something we don't like. This is a rank 1 constraint, so this makes the problem non-convex. So what we did this morning, you ignore these rank 1 constraints, and you end up with a semi-definite program, and you solve this using CVX. Then you do randomization, and you're trying to find a vector V that is such that this vector V has a covariance matrix equal to the optimum V that you computed, but is a feasible V, feasible vector V. Okay, so same as what we did this morning. So this one you're going to have to become a bit familiar, and you will play with this a little bit in the class, and you will see this also in the coursework 3. Right, so once you relax the constraint, you have this. Essentially, this is your SDP, and you do relaxation, and you play with, you implement this in CVX using exactly the same code, essentially as the one I showed you this morning. Right, you can reuse the same code. But what I didn't show you is how to do the Gaussian randomization. Right, so there you may have to go into the papers to find, because the randomization sometimes is very problem specific. So the randomization for this problem may be different from the randomization we have in the MIMO detections, and so on. So it's a little bit problem specific. I don't remember whether in coursework 3 do we have to do this Gaussian randomization? Yeah. So you will have to find a way to do this Gaussian randomization. Right? So again, the idea is that once you have this V, this capital V here, you use this covariance matrix of vectors that are Gaussian distributed, and you create many samples of those that have a covariance matrix given by V, and then you have to normalize and scale them such that they actually satisfy the constraints, right? And then you check them all, and you choose the one, the V, that actually will have the best objective value, objective function. I have a max here. I could have written a minimum of minus this, right? Right. Typically in CVX you expect a minimum, so it would be a minimum of minus this quantity. Right. Right. Okay, so with this we covered LP, QCQP, SOCP, SDP, SDR. And I was saying that this SDR is very useful when you have QCQP, but that is non-convex. Right? And we see this quite a bit in communication. And as you move from, so SDP essentially is a kind of superset of the other ones. Now there is another branch of optimization problem. So if I draw this, you have LP, and then you have QCQP, and you have SOCP, and then you have SDP, right? Now you have another form of optimization, convex optimization problem that do not look convex at first sight, is an LP, and then on top of this you have what is called a GP, a geometric program, right? So this is a different kind of class of problems that do not look like any of the one that we had discussed before. And this is this GP, so geometric program. And the formulation looks a little bit more ugly in the sense that it plays with those quantities. So this is quantities where you have a vector x, you have a function that is a function f that is a function of a vector x that is certain dimension n. The entries of x are given by x1 to xn, and they're all positive entries, strictly positive entries. And I have a coefficient c here that is positive, and the exponents here are real. Right? So for instance, you would have x1 power 2 multiplied by x2 minus 1 multiplied by x3 1.3, for instance, right? Those x1, x2, x3 would have to be positive, right? And then I can have a constant here in front, this c that I have there, that would have to be positive, right? So this is called, in the context of those, optimization problems, this is called monomial. This is a monomial term. And then you have a polynomial is when you take a sum of monomials. So you have k terms that look like this, and you sum them up. Okay, so this is typical, terminology that have been used over the past few decades on this kind of terms. And the monomial and polynomial, they have some interesting properties. Is the following: if you take a quantity like this, and you multiply this by a term like this, you still end up with a polynomial. So you take this, something like this, you multiply by something like this, you will still end up with a sum of quantities where this quantity here is positive, and all those terms will be fine, all those x will be positive, and all those upper terms here will be real, right? So if you take this and you multiply by this, it's still polynomial. If you take this and you divide by something like this, so you take a polynomial, divide by a monomial, you still have a polynomial. Same way, right? So those are actually just useful properties. And what we have in the context of geometric program, we have actually an optimization problems where the objective function looks like that. And the constraints can look like that. And so there are many examples where you will see this is clearly non-convex. I think I gave you an example before where I think we have x squared divided by y, right? And I showed you this is actually convex. This is a particular instance where you have two entries here, but this is convex, and so we had this. If you go back, was it here? Yeah. Do you remember this one? So this is one quadratic over linear. This is convex, and you can show because your Hessian is semi-definite positive. But this is really a particular case, and there would be many scenarios or many choice of your exponent there for which you actually don't have a convex function. Right? Okay, so how you deal with that? So apparently it looks not convex, but there is a way to get around that. So you can reformulate the problem. So this is what we have. This is our GP problem. We have, again, this kind of formulation, same as classical optimization problem, but the particularity is that my F0 is now polynomial. The Fi, the inequality constraint here, are all polynomial. And I have an equality constraint here that is a monomial. Okay? So this is the particularity of those. This is polynomial, and this is monomial. And this is clearly can be very non-convex because of the structure of the monomial and the polynomial. But what we can do, we can transform this into a convex form. So how would you do that? Well, you do a change of variables. So you take your x, and you say, well, xi will be now exponential of y, right? So if I'm writing this down, so I have, right, so I have xi is e of e to the power yi. And so now if I have my function of x is c x1 a1 all the way to xn an, this is like c e y1 a1 all the way e yn an, right? And the c I do a change of variable, and I say C is equal to e to the b. So I create two new variables, y and b, and so this is e to the b plus a1 y1 all the way plus an yn. This is my f of x. Okay? And so this is something that looks already something we feel a bit more comfortable, because now if you take a log of this, if you take a log of f of x, then you end up with something that is linear. Right? Is linear in all those variable y. Okay? So this is what we try to do here. And you do the same, this was for the monomial, but can you do the same for the polynomial? So if you have the polynomial, now you have something a bit more complicated. You have your f of x is now a sum of terms like this, right? So you're going to have a sum of terms like that. So e, I don't know, you have a k there, and that's why you're going to have argument k there, right? So every time you're going to have something that is EB argument K plus A1 argument K, Y1 plus all the way, right? So you're going to have many terms there, right? But you're going to have a sum there. And so if you do a log of this, if you do a log of this term, then you bring a log here, and you end up with a log of a sum of exponential of something that is linear, right? So imagine this is a linear function, so this is convex. Log some exponential, this is convex as well. This is something I mentioned earlier in the module. We have not shown that, right? But I mentioned that if you have a function that looks like this, this one, log sum exp, the log of a sum of exponential, right? So this is a particular case where the exponential here is exponential x1 plus xn, but you could have, in general, you could have a linear function there. And this is what we have there. And this one you can show, this is in the book, you can show this is actually a convex form. And so how would you show this? You would have to compute the Hessian of f, and you can show that the Hessian is semi-positive definite, right? That would be one way of showing it, probably the easiest way. But it's a little bit lengthy to show. But you can do that. Right, so now we end up with, if you can take a log of this function f, you end up with a log sum exponential of a linear function. And this is nice because this is convex. So the GP, what it does, if you have a GP with those polynomial and those monomials, what you try to do is that you do a change of variables such that your x becomes exponential of y, your c, your constants that is positive becomes exponential b. And then you have terms that are function of a linear function of your optimization variable y, your new optimization variable y. And you apply a log on the objective function and the constraints in order to linearize or to convexify those functions and those constraints. Okay? So now we can do this. You can bring this into the objective function, and you can do this into the constraint, and then you have reformulated the original GP into a transformed GP, which now looks like this. I minimize now the log sum exponential. This is convex. I had a polynomial here. This is now log sum exponential again. This is convex. And I have here a term that is linear, which is convex as well. So this is actually a convex formulation. And so if you bring this into CVX, then you can solve this. But, and so I was saying that actually this is a general form of here, GP is a general form of LP. So this is your GP and your LP is here, right? And you can see this because if you take your K naught here, this quantity, you take it equal to 1, and this is 1 is equal to 1, you essentially remove the sum, and you end up with a log of exponential, so this is just the argument. So you end up with a linear term, right? And that boils down to the linear program. Okay? So this is a generalization of linear program, but it's a different form than, you know, the QCQP, SOCP, and so on. So where is this used in communication? Well, I will give you one example that is very popular. That will give you also some other examples in other wireless contexts. So the example we have here, it's a multi-cell scenario, and we have seen the system model for multi-cell scenario. But this is a simplified version of this. So it's a multi-cell where I have L cells, and I have a transmitter, I have receivers, I have multiple of them. And I have L of them. And they all interfere with each other. So transmitter 1 wants to communicate with receiver 1, but transmitter 2 create interference to receiver 2, transmitter L create interference to receiver L, transmitter 1 create interference to receiver 2, transmitter 2 receiver. So they all interfere with each other, right? So this is called in information theory, this is the interference channel. And so this is what, we didn't go into the interference channels in this module, but we wrote the system model in the general case where we have linear precoder at those transmitters and can have multiple antennas at the receiver as well. You can write the whole system model. This is what you will have to do in a way in coursework too. Now, what I want to do here, I want to say, well, one way of managing the interference between all those different, you know, cells. So you can imagine this is a cell 1, this is a cell 2, this is a cell 3, and they all interfere with each other. What you can do is you can do some power control. So you have power that is available at those different transmitters, but you want to adjust the power level according to those different channels here, all those different channels. You assume you know them. And if you know all those channel gain to the transmitter, you can adjust the power level at each of those transmitters in order to maximize an objective functions. And for instance, maximize your sum rate. So the sum of the rate of user 1, user 2, user 3, and so on. Right? So this is what we can do. And to do that, we can first write the SINR of each of those receivers. Right? So what will be the SINR of receiver 1? It will be the power of transmitter 1 multiplied by the channel gain of transmitter 1 divided by the noise power that we have here plus all the interference that you see from the transmitter 2 all the way to transmitter L. Right? And this is what you have here. The SINR of user L is the power at transmitter L multiplied by the channel gain between the transmitter L and the receiver L. Right? This, in our notation, is something like this. Is a h magnitude h squared. Right? So, for instance, this could be coming from, you know, relay fading. Right? The magnitude here could be relay distributed, for instance. I have the noise power, and this is the interference term. Right? So this is the power at transmitter P. This is the interference that the transmitter P creates to user L. Right? I have single antenna everywhere, so you don't see precoders anymore here. Right? Good. So what is the sum rate? Or the rate first, the rate of user L is 1 log 1 plus SINR of user L. And what we're going to do, we're going to assume that we are in the high SNR regime. So the SINR is large enough such that 1 is negligible compared to this term. So we assume this term is negligible. Right? It's a strong assumption. Right? But you will see the GP can solve this problem of optimizing the power across all those transmitters. In this case, where we are in the high SNR regime. Because if you remove this, we'll show that actually the problem becomes essentially a geometric program, right? If you have the 1 plus, it becomes much more difficult. But so let's imagine we have this, and this is relatively accurate. Let's make this assumption. So what I have now is I have my network utility function is I want to maximize the rate of user 1 plus the rate of user 2 plus the rate of user L. So I have one user served in each of those cells, and I want to maximize the whole network rate, so the throughput across the entire network. And I'm saying I operate at sufficiently high SNR such that this is actually equal to a sum over L of log 2 1 plus SINR of user L, right? This is a log, and I assume this is, I approximate this. This is the sum over L of log SINR L, and so this is equal to a log of a product of SINR L. Okay? So what I end up doing, if I want to maximize this, it's equivalent to just maximize the product of the SINR. Okay? And this is what I have here. I have the product of the SINR, and that I'm writing now. This is the SINR of user L, and I want to maximize the product of those SINR. What are the optimization variables? Those are the power levels that I have at each of those transmitters, P1 to PL. And I'm subject to a power constraint that tells me the power that I'm using in the given transmitter has to be smaller than a certain threshold. Okay? Right, so what can we do with this? So once you have that, then you can transform this, and you can say, well, if you want to maximize this term, so I have a max of a product of GLLPL and sum over P different than L of GLP PP plus some noise, right? And I'm subject to some constraints, right? So I'm going to use again the same trick as what we did before. I will introduce some new variables t here, right? And I will say, I will formulate this differently. I will say this is equivalent to saying I want to maximize a product of new variables, a product of t, from 1 to L, of variable TL. And I will say, now each of those quantity here has now to be larger than TL. So if I maximize each of those terms, I will actually maximize the TL. If I maximize the TL, I will maximize each of those terms. So I'm saying this is GLLPL divided by sum GLPPP plus this square is larger than TL. Right? This is one way of doing this. So, okay. So now I have a maximization of this subject to this. I may want to change a maximization into a minimization. So how can I minimize? I can say, well, to minimize, this is the same as saying this is the min of 1 over this. Those terms are positive. Those TL, they have to be positive. I have over PL and TL. Those TL has to be positive. And so this is the same as saying this is a minimization over the inverse of those TL. Right? And I'm subject to some constraints. Okay, so this is all this is now here. I have a minimization over a product of 1 over this TL, and this is what I wrote here. Right? Minimization, the product of 1 over TL is the same as maximization, the product of the TL. and I'm subject to this constraint that I rewrite slightly differently like this. It's exactly the same thing. It's just written differently, right? Your TL is there, and you bring this term on this side, essentially, and you divide by this. So you end up with something here that is smaller than 1. Okay? This is exactly the same as this, but written differently. But what do you see here? What is your objective, your variables? You have P and T. This is a product of 1 over T. So this is like a monomial, essentially. I have those x1, x2, x3, and so on, right? So here I have those t to the power minus 1, t1 power minus 1, t2 power minus 1, and I just multiply. Here, what do I have? I have a product pp divided by pl. So this is like pp to the power 1 multiplied by pl to the power minus 1. And I have a sum over this. So this is like a polynomial. Right? I have a sum, essentially, of monomials. Right. So we have here a GP form. This is nothing else, actually, a GP, a geometric program. And you can convert this into a convex form by doing the change of variables, and you end up with essentially a convex form of this GP program that you can solve, optimally. So this will give you the optimal solution of this power allocation across those different cells, assuming that you are in the highest NR regime. Right? So this can be done also in massive MIMO, in self-free massive MIMO. So in massive MIMO, when you have those many antenna, you have also power allocation problems among different users. And if you're in the highest NR regime, you can also show that you can approximate this problem, and you end up with a geometric program to allocate the power across different users. Okay, so there are other examples. I give you here another examples. I will not go into those details, but so this is something else we did in the past many years. No communication, or at least at first, is just doing wireless power transfer. So you use radio waves, but to power up devices. Right? So you have a transmitter, you have a wireless channel, and you have a receiver. And what you want to do is you want to design your signals at the transmitter, the one that you will broadcast. You want to design them in the most efficient way so that you can maximize the amount of DC power that you deliver at an output of an energy harvester. And so what it does is that you have, let's say, Internet of Things device. The Internet of Things will want to be completely autonomous. So you want to charge this using your Wi-Fi or your 5G system. And the question is, how would you design the transmit signal in the most efficient way in order to maximize the amount of power that you deliver at the output of the energy harvester? So this power here can be stored in a battery, for instance, so that your device becomes completely autonomous. Right? And so what you can show, you can design waveforms here at the transmitter in order to maximize this as a function of the channel. And this guy here, the receiver, is a nonlinear device. And you can show that this, finding the optimal waveform that maximizes the power of the receiver, can be formulated using geometric program. It's a bit more complicated, a geometric program, because it's actually a succession of approximation of a geometric program. And then what you can do as well, you can say, well, what if now I have a transmitter, I have a receiver, but I want to deliver information and energy. So I want to communicate with the device, but I also want to charge the device simultaneously. Right? So there you have power transfer and you have communication at the same times. And those two they're not the same. So you use the radio waves on one hand to deliver information, but you want to use the same radio waves to charge the device. And so the waveform that you use at the transmitter may be good for communication, but may not be good for power transfer, or inversely. And the question is, how do you choose the signals at the transmitter in the most efficient way to deliver power and energy simultaneously, right? And so there, you'll see in those papers, if you're interested, this can be also solved using geometric programs. There are also some other solutions using semi-definite programming or SDR. And then you can combine this with RIS, so this intelligent surface added system design, where on top of having within this wireless channel, you have an intelligent surface also that will help to deliver energy to the receiver. And so then you have to design the waveform and the transmitter together with those coefficients of the intelligent surface in order to maximize the amount of energy that you deliver or maximize the communication performance, right? So this is some of the work that Yang did also recently. Right, so those are examples where we really use GP and SDR quite extensively to design these kind of systems. Okay, so with this, we have covered, I think, the most common form of convex program. What I want to show you now is how you can use optimization theory, namely Lagrangian duality and KKT conditions, to, in some scenarios, find the optimal solution to a problem. And this is to answer your question that we had this morning. In some cases, for instance, we use for the power minimization there, when you have this unicast beamformer, we used SOCP and SDP. But we can also, from optimization theory, we can actually find the structure of the optimal precoders in semi-closed form. So some part needs to be still numerically computed, but some parts we have some closed form solution. Some other application is like when you do the water filling. So there, in that case, this is a convex problem. So you could write this into CVX and then numerically find a solution, but actually you can obtain a closed form solution of the problem as well, thanks to this Lagrangian. Okay? So the Lagrangian starts with the following. We have the original problem, same as what we have been playing with since the beginning. We have an objective function, so we have a constraint, inequality constraint, and we have an equality constraint. But I do not make any assumption on the convexity of the problem. So this could be a non-convex problem, right? And I'm saying the optimal value of this objective function is denoted as P star. That's the global minimum, right? So I may have a problem that is non-convex, for instance, something like this. But this is the optimal value. So this is my P star, essentially. And what the Lagrangian does, Lagrangian is a way to, under some condition, find the global optimum of this. So it will try to give you, under some condition, whether some of them are necessary, some are sufficient, whether you can actually find what are the necessary and sufficient conditions for this P star to be a global optimum. That's what they try to do. And so what the Lagrangian does, it says, well, I have this optimization problem subject to constraint, and I want to replace this by an unconstrained problem. So I create a new objective function that is a linear combination of the actually objective function f naught and the constraints. And so I'm saying now I have this Lagrangian is my objective function plus a weighted sum of the inequality constraints plus a weighted sum of the equality constraints, right? And the weights here are called the Lagrangian multipliers, lambda and mu. So lambda for the inequality constraints and mu for the equality constraints. And essentially what you will try to do here is to say, well, we know the notion of when you have an unconstrained problem, we know how to find a global optimum solution. You typically take a derivative of this, and you're looking at when it's equal to 0, right? So if you have an unconstrained problem, you're looking at what is non-equal to 0. This is equal to 0. You say, oh, this may be a minimum. If it's equal to 0 here, that may be a minimum. But because it's non-convex, you're actually going to have to check among all possible points to see whether actually would be the minimum. So the Lagrangian here, what it will try to do, it will try to generalize this notion of stationarity that you have in unconstrained problem, where you take the derivative and you say this is equal to 0, this will be actually the point that achieves the minimum. It generalizes this to the context of, constraints optimization problem. And so the notion of derivation of the objective function and making this equal to 0, as we know when we have one-dimensional or unconstrained problem that is convex, will be generalized here, where we actually take a derivative of the Lagrangian with respect to those parameters, and we will try to equate this to 0 as well. So this will come in a moment. So what you try to do here, intuitively, you say, here, actually, I have very strict equality and inequality. And you try to replace this problem by kind of soft problem, where instead of saying it has to be below 0, here I'm replacing this by a kind of soft, not soft constraint, but by a kind of price. So I want to minimize this function, but imagine that this quantity is positive, so it's not negative, so it's positive, so I violate this condition, and this lambda is positive. I essentially, if this is positive and this is positive, it will be as if actually I'm now maximizing an objective function that is actually higher than the original one. So I will be penalized if my constraint is actually violated. Right? So this is the idea behind the Lagrangian. So you will see this as time goes by. So for the time being, just imagine I start with a constraint optimization problem, but I now convert this into an unconstrained problem. So I don't see the constraint anymore. Everything is reflected into this weighted sum of optimization function and constraints. Right. So the next step is to say, well, let's try to find the value of x that minimize these Lagrangian. And this new optimization problem, which is equal to minimizing the Lagrangian with respect to x, this would give you an objective function that is a function of the two Lagrangian multipliers. This is called the dual function. And what is very interesting with this function is that this is always concave. And the reason why this is concave is because the Lagrangian here is a linear function in lambda and mu, right? Lagrangian is a linear function if these are your parameters that you want to your function of. This is linear function if lambda is linear function in mu, right? And you minimize with respect to x. So if you have a family of linear functions in those two parameters, and you minimize over all x, what you do is that you do a pointwise minimum of linear functions. And so maybe you remember what we did at the beginning. If I have a pointwise minimum of concave functions here, I have two concave function of x. If I take a pointwise minimum, so for every values of x, I take the minimum between those two, this will still be concave. So this is what we have now with the Lagrangian. We have a pointwise minimum of linear functions, but those linear functions are, concave functions because they're linear. So you can argue this actually will still be concave. And this is where it's interesting, because now even if your original problem is non-convex, the dual function, so this g function, is always concave. So now my g here, my g function g is concave even if the objective the original problem is actually non-convex. And this lambda and mu, so those are the Lagrangian multiplier, and they are called, they say that actually we say those two are actually dual feasible if the lambda is always positive or equal to 0. So the Lagrangian multiplier attached with the inequality constraint has to be positive, and this quantity has to be finite. And what is interesting is that this is always smaller than that. So why is that the case? Is because if you have this L here, right, and your G is the minimum over X, so for all values of X, your G function will always be smaller than in quantity, right? That makes sense. So G is always smaller than this because G is equal to this, but when you take the minimization over X. Now this is always smaller than the objective function, F0. Why? Because if you choose lambda and mu so that they are dual feasible, that means actually lambda will be positive. If lambda is positive and you choose a feasible vector x, what does that mean? If lambda is positive and x is feasible, that means actually if x is feasible, fi of x has to be negative by this constraint. So this will be negative and this will be positive, right? So this term will always decrease this term will always decrease this value. So this value will always be smaller than this because this term will be negative, essentially, right? And this is why you have the second constraint here, right? So you can say for any x, my dual function will always be smaller than my objective function. And this holds for all x, and so it will hold for the optimal values of x, the one corresponding to the global minimum. So you can say that the dual function is always smaller than the GP, the P star. So what that means is that if this is your objective function f naught of x, you create with this g, you create a new function that is always concave, and this concave function g will always be smaller than any values that you have in f naught. Will be always a lower bound on this optimal value P star. Okay? So you have, this is sometimes called the primal problem. So this is your original optimization problem, your objective function, and you find another function that is called dual, for which you can show that this quantity is always a lower bound of the existing, of the primal problem. And this lower bound here, this gap between those two, will be a function of the parameter lambda and mu. So what you could do is to optimize lambda and mu so that this gap decreases, right? So you could choose lambda and mu so that you maximize this, you increase this function, and so you decrease this gap, right? And this is what is done here, just in a moment. So this is an example here. This is your objective function. This is your f naught. This is your constraint. And your constraint says that function has to be negative. So you see that actually your 0 is here. So between this point here, minus 0.5 roughly, and 0.5, this constraint is negative, right? And this dot here is the optimal value, so is the P star. So is the point that minimizes this objective function subject to those constraints, subject to the constraint being negative. And all those dashed lines here are obtained by looking at this Lagrangian for different values of theta. And you can show that for whatever values of theta, you always find this dual function is always smaller or equal to the objective function, right? So this theta essentially reflects this quantity here. For any values of x, you always find that your dual functions will be smaller than the objective function. So this is a way to represent it. But let's come back to this problem. So I have here my primal problem. I have this dual function, and I want to find the gamma, the mu, and the lambda so that I can decrease this gap as much as possible. So I can create another objective function or an objective problem optimization problem where I want to find the lambda and mu that maximize this G. And this would be the best lower bound on this optimal global optimum P star. This is what you have here. You want to find lambda and mu that maximize these dual functions subject to feasibility, and feasibility means that your lambda has to be positive. Right? And so this gap, if the value of this problem is called D star, so this would be here, this is my D star, this value here is called D star. This gap here is called the duality gap. And if you have a convex optimization problem, you can show that this duality gap is equal to 0. And so that means that when you have an optimization, convex optimization problem, you can find a lower bound on your optimization problem that acts as a proof that your optimal value is indeed matching the maximum of this dual problem. And the gap is really close. So this is very useful whenever you try to demonstrate that a given problem is actually global optimum. One way of doing this is saying, well, I have computed my dual problem here. I have found that my value, the optimum value here is equal to D star. And if you find that your objective functions here has a minimum at P star that is equal to D star, you know that actually this has to be the global optimum. Because this one always acts as underestimator, or actually a lower bound on the original problem F naught. Right, so this is a bit more involved, but this is essentially the idea. You can have weak duality and strong duality is when you have this gap is equal to 0. Weak duality is when the gap is non-zero. And when you have convex optimization problem, under some tiny conditions, you can show that actually you always achieve this strong duality. So you can find a dual problem, and you can optimize your dual problem so that actually the optimal solution to this dual problem the value is equal to the one of your primal problem. And so this dual problem acts a kind of proof or certificate that indeed your lower bound here is matching the upper bound of the dual problem. That's the idea. Right, so let me show you an example here of how you can compute this. And I will take the example that we had early in the module. So let me take this linear program that we had, where we have this. So we had a linear objective functions. We have an equality constraint, and we have inequality. So x1 and x2 have to be positive. So let's write the Lagrangian of this. Let's solve the Lagrangian. And from the Lagrangian, from the dual function, let's try to find that the optimal value is indeed located at 0, 1 here. So how can I write the Lagrangian? I say the Lagrangian is the objective function minus something multiply these constraints, plus something multiply these constraints, plus something multiplying this inequality constraints. So we're going to have 2 lambda 1 for x1, lambda 2 for x2, and a mu for the equality constraints. Right? So let's write this. And let's write the duality function, dual function. Right. So I'm here. So I have, this is x1 has to be positive. So minus x1 has to be negative. So I have my objective function is in the constraint I have minus x1 has to be negative, minus x2 has to be negative. Right? So now I multiply by lambda 1, whose ideally is positive. Right? So this one and this one will be positive. And now I have the equality constraint here. And so this is my Lagrangian. And I can compute the dual function from this by saying I want to take this, I want to minimize over x. So I want to find the x that minimizes this quantity. And so I have a constant here, 2 mu, that comes in front, and then I have a minimum of this term here. And so what you see is that x1 and x2 now is just in the real domain. I do not capture any constraint anymore onto x1 and x2 because they already capture here in those Lagrangian. And what would be the minimum of this quantity? If this term is equal to 0 and this term is equal to 0, then this will actually always be equal to 0, and I'm going to have the minimum will be equal to 2 mu. So I have 2 mu if this term is 0 and this term is 0. This is what I'm writing here. And otherwise, if this is non-zero or this one is non-zero, I could choose x1 or x2 to be minus infinity so that this whole term becomes minus infinity. Okay? So my dual problem, so it's written differently, is I have now my dual function that I want to maximize over my Lagrangian multiplier. So I want to maximize this objective function here, the dual function, subject to those constraints. I have the first constraint here and the second constraint here. And you can show from this very easily that here you have mu has to be smaller than 1. Here mu has to be smaller than 1 over 2, right? So smaller than 1, smaller than 1 over 2. So you better choose mu equal to 1 over 2 in order to maximize this term there. And so you end up with mu is equal to 1 over 2. This objective function here with mu equal to 1 over 2 will be equal to 1, which correspond to the objective function that we had earlier on when we computed just based on the geometric drawing. So this is an example where you have a convex optimization problem, because this is a linear program, where you show that the dual function, the dual optimization problem, indeed has an objective whose value, so global optimum, is actually matching the global optimum that you have from the primal problems. Right. So let's move on. So how can you do this for a general optimization problem? And maybe let me have a 5 minutes break before we get into this KK2.